Hello there, Mr. Sutton here, bringing you the Algebra 2 Honors 8-7 lesson on binomial distributions. In this one, we will be constructing and interpreting probability distributions, and we're going to find probabilities using binomial distributions. So we're just going to dive right in with a problem here. Let's let x be a random variable that represents the sum when two six-sided dice are rolled. Make a table and draw a histogram showing the probability distribution for x. Okay, what does all this mean? So let's start with this whole random variable thing, which sounds kind of weird. A random variable is a variable whose value is the output of some probability experiment. So for example, we could make a random variable for flipping a coin, and then the value of that random variable would be heads or tails. In this experiment here, we have these two six-sided dice being rolled. So the values would be all the different sums that we could generate from that. Now, they also talked about a probability distribution. What's that? So a probability distribution is a function that gives the probability for each possible value of your random variable. So let's say that we figured out all the probabilities for the different sums you could get from rolling these two dice. We could just make a function that links those up. So let's say that I plug in the number 3, the sum 3, into my probability distribution, and it'll tell me the probability of getting a 3 when you add up my two dice. So that's what we're after here. Now, we're about to go ahead and do this, or you're about to go ahead and do this. Some advice I would give you is, first off, find the frequency of each outcome, and then if you know the total number of outcomes, that would be helpful for the next step, which would be finding and graphing the probabilities. So I would recommend you make a table, first with the frequencies and then put the probabilities down below. And just as a little bit of a heads up, because we're covering all the possibilities, all of your probabilities in your p of x function that you're going to graph here should add up to 1. So with that said, pause the video. Make a table for all the possibilities and frequencies and probabilities, and then if you can draw a histogram with all that, bully for you. All right, let's see how that went. So my table representing all the different possible sums, if I'm rolling two dice, I can't get a 1 because each die has a minimum value of 1, but I could get at least a 2. And then I can get all the numbers up through 12. That would be a 6 and a 6. So here is my little table that I'm putting together. 2 through 12 for the x, that's the variable here, giving me the sum that I'm looking for. And now here are my frequencies and probabilities. So the frequency of getting my dice to add up to 2 is just actually going to be, there's only one way to do that. That's if you roll a 1 and a 1. To get a 3, I could do a 1 and a 2 or a 2 and a 1, so that's two different possibilities. For a 4, I could do a 1 and a 3, a 2 and a 2, or a 3 and a 1. So that's 3. And I think you kind of see where we're going with this. We have one more possibility each time. So there's 4 ways to get a 5, 5 ways to get a 6. And to get a 7, you could get that with every number 1 through 6 if you match it up with another number on the other dice. So there's 6 different ways to get a 7. Now, we go back down as we go on to the higher numbers. So an 8 is kind of like a 6. There's only 5 ways to get that. 9, you can only get 4 ways. 10, you can get 3 ways. That would be if you had a 4 and a 6, a 5 and a 5, or a 6 and a 4. There's 2 ways to get an 11 and a 12. That would be double 6s, so only one way to get those. Now, if we add all these up, we could just quickly go on Desmos and do that if you don't already know what they add up to. So 1 plus 2, 3, 4, 5, 6. And then 5, 4, 3, 2, 1 adds up to 36. So when we do our probabilities, we're just going to take our frequency and divide each of these by the total. So we've got 1 over 36, 2 over 36, which reduces to 1 over 18, 3 over 36 reduces to 1 over 12, 4 over 36, that's really 1/9. 5 over 36, can't reduce it. 6 over 36 is 1 over 6. And then we go back down, so 5 over 36, 1/9, 1/12, 1/18, and 1 over 36. It's nice. It's a nice symmetrical looking situation here. All right, so let's make a histogram now, putting all this together. For my horizontal part of my histogram, I'm going to be doing just the sum. So this is the value of the random variable, always goes on my horizontal here. And then for the vertical, that's all these probabilities. And it's kind of hard to see the way that I've written these out, but my grid lines here are going by 1 over 36. So again, this 1/18 is 2 over 36, this is 3 over 36, and so on. And the highest we can get, we've seen from our table, is 1 over 6 or 6 over 36. So just doing my histogram, 2 goes up to this 1 over 36, 3 is going to be 2 36ths, and then 4 goes up to the 3, 5 goes up to the 1/9, 6 goes up to the 5 over 36, 7 goes all the way up to 1 over 6, as we can see in our table, and then it just goes symmetrically back down, going the other direction for each of these. And then we have 12 going up to the 1 line there. And there's our histogram showing the probability distribution for rolling 2 6-sided dice. So now that we've got this beautiful probability distribution, what can we do with it? Well, we can answer questions like these. So this first one here, they're asking what is the most likely sum when rolling 2 6-sided dice? And then in the next question, what's the probability that the sum of 2 dice is at least 10? So now that you've got all these probabilities broken down, you can mix and match them any way you want to answer these questions. So pause the video and see if you can answer these, and then we'll bring it back together. All right, so let's take a look at part A, most likely sum rolling 2 6-sided dice. So this one's pretty straightforward. We just want the highest probability. Going through our P of X row here, we see that that's 1 over 6, or if you're not great comparing fractions, you could just look at the frequencies and see that we have the highest frequency when we are looking for a sum of 7. So 7 is the most likely result, 1 over 6 probability. Now for this next one, probability that the sum of 2 dice is at least 10. Well, we're asking basically what's the probability that we get a 10, an 11, or a 12, all the things that are 10 or higher. Now that we know the individual probabilities of these, we can just add these 3 things together. And when we do this, you'll probably want to get a common denominator. So this is, again, going to be 3 over 36, 2 over 36, and 1 over 36 can stay the way it is. So adding these up, we end up with 6 over 36, which we can reduce to 1/6. Let's take a look at 2 more examples that are a bit different from what we've seen thus far. In one, we're calculating probability of flipping a coin 20 times and getting exactly 4 heads. And in the other, we want the probability of rolling a 2 or 4 exactly 1 time in 6 rolls of a 6-sided die. So on the face of it, these don't seem like they should be super tricky. I mean, with this coin flip, why don't we just do the probability of a head, 1/2, and raise that to the 4th power, right? 4 flips. But that would give us the probability of 4 heads in 4 tries. If we want the probability of 4 heads in 20 tries, then we need not only the 4 heads, but we also need the probability of 16 tails to go along with it. So we'd be doing probability of the 4 heads and multiply that by the probability of the 16 tails. Even that wouldn't quite be good enough, though, because that would just give us the probability of getting the 4 heads in the beginning and the 16 tails right after. They'd be in a row. But what if one of our heads comes in the beginning and the other 3 come at the end, right? And what about all the other possible combinations of 4 heads and 16 tails that we have to take into account? So in order to take into account all of this, plus situations like this dice roll here, where, success and failure aren't even the same probability like they are up here, to take all of that into account, we're going to need something a little bit stronger. So this is where binomial distributions can help us out. A binomial distribution is just the probabilities of the outcomes of a binomial experiment. Now, that isn't super helpful in terms of explaining what this means, so let's dig a little deeper. What is a binomial experiment? It is an experiment that meets 3 conditions. First off, there have to be n independent trials, and n can be any integer, probably good if it's more than 1, but whatever. The key, though, is they need to be independent trials. These need to be trials that are happening over and over again that don't affect each other. So, for example, flipping a coin is a good place to use this, or rolling a die. In contrast, drawing cards out of a deck and not putting the cards back would not be a good use of this, because every time you do that, you're affecting the outcomes for subsequent trials. So that's one condition. Another condition is that it has to have exactly two outcomes, and this is where the binomial part comes in. Two outcomes, success and failure, however we define that. Now, these two outcomes don't have to necessarily be equally likely. They could be, like in the case of heads versus tails, but they also could be very different, such as in the case of rolling a 2 or a 4, or rolling any of the 4 other numbers on the die. But we need to have exactly two outcomes. So there can't be any alternative to success and failure. And then the last thing is that whatever those probabilities of success and failure are, they have to be the same probabilities for success and failure each time. So whatever the probability of success is, we're going to call that P in the formula that we're about to use. And now, if the probability of success is P, what's the probability of failure? Well, it's going to be the complement of P. It's going to be 100% minus whatever P is, or 1 minus P if we use non-percentages. That's the probability of failure. So given all of this, if we meet these conditions, what's the payoff? Well, the payoff is that we're allowed to use this super handy, actually pretty quick formula for calculating the probability of k successes over the course of n trials. And I'll call this P of k. So there's three parts to this formula. In the first part, we have n choose k. So we have all the combinations we can form from a list of n, a length n, with picking only k of those. Now, the next part of this is we're going to take the probability of success, P, and raise that to the number of successes, to the k, so P to the k. And the last part is we also have to take into account the failures, because with this one, with getting exactly 4 heads, we don't want to get more than 4 heads. So to get the failures in there, we need to do 1 minus P raised to the number of failures, which would just be n minus k. So 1 minus P to the n minus k. So this formula looks a little bit crazy, but it is actually very efficient compared to the alternative, which would be writing out all the possible flips that you could get flipping a coin 20 times, and then counting up how many of them gave you exactly 4 heads. That would be a huge nightmare. Instead, we're going to use this formula. So with all of that said, pause the video and give this formula a test drive on example 3. All right, so for example 3, my n value here is going to be 20. The k value is 4. We want 4 heads. So we have 20 choose 4. And then the probability of success, that would be probability of heads, that would be 0.5 or 1/2. And the number of successes, again, would be 4, so 0.5 to the 4th. The probability of failure would be 1 minus 0.5, which also just happens to be 1/2. And the number of failures would be 20 minus 4, or 16. So we just have to plug all this into the calculator. So here's my Desmos. Again, to get combinations, we can do n capital CR parentheses, and then here we need 20 comma 4 to make that happen. So that's the number of ways to get exactly 4 heads, or 4 tails. It actually is the same combinations. And then we need to multiply that by these probabilities. So we're going to do 0.5, raise that to the 4th. And we'll also do 0.5, raise that to the 16th. Now, I know some of you might be thinking, couldn't we have just done 0.5 to the 20th? In this case, yes, but we're not always going to have the same probability of success and failure, so it's good to get in the habit of treating these separately. And our final outcome, if we round it off to 3 decimals, is 0.005. So we have a 0.5% chance of getting exactly 4 heads. All right, so let's try this next one out now. Pause the video and give this die a roll. Okay, so we're looking for the probability of one success out of 6 trials. So P of 1. That's going to be 6 choose 1. The probability of success in this case is, since we want a 2 or a 4, and there's 2 possibilities out of 6 total that work, that would be 2 out of 6 or 1 out of 3. So we have 1/3 raised to the k power, which k was 1 in this case, so 1/3 to the 1. Probability of failure is 1 minus 1/3, so 2/3. And the number of failures that we want, if you could say that, it would be the 6 minus 1. We want 5 failures, so 2/3 to the 5th. And now let's just multiply all this out on the calculator. So on the calculator now, we're going to do NCR, parentheses, 6 comma 1. And we'll multiply that by, let me do parentheses, 1/3 raised to the 1. I mean, I don't really need to raise it to the 1, but whatever. And then we do another parentheses with 2/3, and we will raise that to the 5th power. And that all comes out to 0.263. So there's a 26.3% chance of getting a 2 or 4 once in 6 rolls. Now that we've seen the binomial probability formula in action, we're going to use it to construct a binomial distribution. So here's our problem for this one. According to a survey, 60% of teens 13 to 17 in the US say they spend time with friends online daily. You randomly choose 6 of them and ask them whether they spend time online daily. We want a histogram of the binomial distribution for this survey. So what are they actually asking for? Well, they would like a histogram that shows you what's the probability that 0 out of your 6 teens says yes to this question. What's the probability that exactly 1 says yes, that exactly 2 say yes, and so on for 3, 4, 5, and 6. So they want each of those different probabilities. Each of those probabilities is like one of those questions that we answered in the last 2 examples, where we basically have a binomial experiment going on. So to make our lives a little bit more efficient here, what we're going to do is we are going to create a Desmos function that lets us input the number of successes, 0 through 6, into the binomial probability formula. We'll custom fit it a little bit for this problem, but we're going to be starting kind of with your regular binomial probability formula that you saw in the last couple of examples. So pause the video and see if you can come up with a function that allows us to do this. And you're going to have to think about what you want your x to be. All right, so if I'm looking for something that lets me plug in number of successes, I'm going to write this as p of x, and x will be my number of successes. Now the first part of our formula was n choose k. K was the number of successes. So I'm going to start this formula with p of x equals 6, because we have up to 6 who could say yes, up to 6 possible successes. 6 choose x, the number of actual successes. The probability of success is 60%, or 0.6. And again, the number of successes we're looking for is x. So 0.6 to the x, whatever x is, 0 through 6 we could plug in for this. Probability of failure was 100 minus 60, which would be 40%, or 0.4. And the number of failures would be 6 minus whatever this x is. So 0.4 to the 1 minus, or 0.4 to the 6 minus x. All right, so what do we do with this? Well, again, we're just looking for the probabilities if we plug in 0 through 6 for this thing. So just plug each possible number of successes into this function, make a table out of that, and then use your table to make a histogram. Go ahead and give this a shot. All right. So let me create the beginnings of my table. I've got the number of students who are saying yes to the question when I randomly ask them, and the probability that that actually happens. Here's Desmos. Let me create this function in here. So I'm literally just going to write in exactly what I've got written here. So p of x equals, and then, well, I have to modify it because of the formatting of my combination, right? So I need to write n capital C R, and then I'm going to write 6 comma x. There we go. and then I'll multiply that by 0.6, raise that to the x power, and then I'll multiply that by 0.4, raise that to the, to get the whole exponent in there. If you try to write it all in there, it'll knock your negative down to the lower level. So to get that whole exponent in there, you need to actually use a parentheses, and then 6 minus x. That lets us keep all of that in the exponent. All right, so let me press enter, and now I can just start plugging things in. So let me start by plugging in 0. That's about 0.004. So a very slight chance that none of the teenagers says that they engage in this activity. If we plug in 1, that's 0.037. If we plug in 2, that's 0.138. Plugging in 3 gives us 0.276, so that is quite a bit more likely than all the others so far. How about 4? If I plug in 4, that's 0.311, even more likely. And then if I plug in 5, 0.187. And then finally, all 6 of them saying yes, there is a 0.047 probability of that. All right, well, let me make a histogram based off of all this stuff. So on my horizontal, I'm going from 0 to 6. For my vertical, I need to get all the way up. The highest value here is about 0.31. So I'm going to be going 0 to 6 on the horizontal, and I'll be going by 0.05s up to 0.35 vertically. So for 0, we have 0.004. That's barely, that's like half of a fit. That's like a tenth of a grid line. And then for 1, 0.037, that's somewhere around here. For 2, 0.138, that's somewhere close to 0.15. 3, 0.276, that's about halfway between 0.25 and 0.3. For 4, 0.311, that's a little bit above 0.3. For 5, 0.187 is roughly here. And then for 6, this is roughly 0.05, so pretty close to that first grid line. And there we are. So now that we took the time to construct that binomial distribution, let's use it to answer a few more questions. Pause the video and give each of these ones a shot. All right, so question A, what's the most likely outcome of the survey? This is the most likely question, right? So taking a look at our percentages, the highest one was this 0.311. So probability of having 4 teenagers answer yes to the survey was the highest. So 4 teenagers is the most likely outcome when you do this survey. And then the probability that at most 2 teenagers spend time with friends online daily, well, we just need the probabilities of 0, 1, and 2. So we just need these 3 probabilities added together, which I am going to do on the calculator. So we've got 0.004 plus 0.037 plus 0.138, all comes out to about 0.179. So that's it for this lesson on binomial distributions. Feel free to spend some time with your friends, whether it's online or offline. Till next time, Mr. Sutton signing off.